Ben Rubin and Eric Strom, both in the high-speed circuits department, have become familiar with different computers and operating systems during their internship. Here Ben and Eric discuss with Ben's advisor, Paul Thomas, some of the systems that they've learned, such as Unix and Microsoft Windows. Here Ben is using CAD tools to place and connect heterojunction bipolar transistors and resistors. The placement of the devices are organized in hierarchy, the lowest level being transistors and resistors, the gates, subsystems, and finally the whole chip. Good placement and careful connections are an important part of making a high-speed circuit. Arpan Desai and Matt Biederman, Software Systems and Technology, and Albert Chang, also of the High-Speed Circuits Department, look at a plot with Ben, Eric, and Paul. Paul explains to the group how the large subsystems go together. The pad frame is where external connections are made, and inside the pad frame is where all connections are made between subsystems. These high-speed circuits will be used in high-speed communication links such as the ARPA, Thunder, and Lightning program. Annalise Keene, Design and Reliability, is part of a team doing basic research on novel reinforcement architectures for energy-absorbing structural composites. Her contribution is in materials processing, such as the work shown here. The ultimate goal of this research program is to produce strong, energy-absorbing structures by combining two materials in such a way that damage will be distributed over the whole structure when it fails rather than localized to a small region. To demonstrate the feasibility of constructing such composites, Annalise has fabricated fiber-reinforced epoxy specimens for mechanical testing. Glass, carbon, and Kevlar fibers have been used to find out how different reinforcing materials affect the composite strength, stiffness, and energy absorption. Here, Annalise, along with her advisor, Janet Davis, is mixing an epoxy resin and hardening agent. She will then pour these liquids into a mold which contains the fiber arrangement. The mold is then put into a vacuum chamber, and later the epoxy is converted to a transparent solid by a low-temperature heat treatment. As you can see here, the complex fiber arrangement can easily be seen in the final composite. Christopher Hartman, Interfacial Processes, and Brent Waters, High-Speed Materials and Devices, look on as Annalise and Janet describe the process. Janet explains how the distribution of irreversible damage, which accumulates in a material as it begins to fail under load, affects the total amount of energy absorbed. Distributing the damage uniformly throughout the entire specimen volume will increase its toughness. This concept is being investigated for a variety of containment applications. Tammy Beitzel, Display Components Technology, and Irene Chen, Optical Devices, look on as Matthew Paul, Sensors and Spectroscopy, and his advisor, Paul Coburn, show them what Matthew has been working on as a YMP intern. Matt has been interfacing an instrument that measures resistance as a function of temperature of thin film samples to a Macintosh computer. Resistance measurements can be made both at elevated temperatures and at cryogenic temperatures. Paul explains the cryogenic apparatus to Tammy and Irene. This is a helium-based refrigerator used to cool the sample down to minus 260 degrees centigrade. The samples are first loaded onto the top of the refrigerator, and then the air in the chamber is pumped away with a vacuum pump. This equipment previously was used during the development of high-temperature superconducting films. Today it is being used to characterize many novel phase transition materials. For high-temperature measurements, the samples are placed into a uniform temperature enclosure as you see here. A heating mantle and a water cooling system are used to vary the temperature up to 100 degrees centigrade. Matt loads the sample for testing. This sample is vanadium dioxide film on a silicon substrate, which is being characterized for use in infrared cameras where the temperature dependence of the resistivity is directly related to the sensitivity of the camera. Data is analyzed as it is being accumulated. This data is then stored for later analysis. The films that are being developed at the Science Center are useful for such applications as bolometric infrared imaging cameras and microwave switches. This is a 3-inch mercury cadmium telluride wafer processed for infrared imaging applications. MCT is an infrared semiconductor material which, when processed into PN junction diodes, detects infrared radiation. Two-dimensional detector arrays produce an infrared image. 3-inch MCT wafers are being grown and processed routinely in the Science Center MCT process line. This process was successfully transferred from Rockwell's Autonetics and Missile Systems Division earlier this year. As a YMP student, John Robinson has been working with the MCT process line. This process takes place in a Class 100 cleanroom environment. The lighting is ultraviolet with UV-absorbing blocking filters. Here, John is examining a processed MCT wafer under the microscope and mapping the wafer onto the computer. The wafer map on the computer screen identifies material defects and processing-induced abnormalities. Such maps, obtained at different stages of processing, provide a history of the wafer and help identify the process limiting steps. John, along with one of his advisors, Jagmohan Bajaj, explained to fellow YMP students Dennis Hong, Image and Signal Processing, Uday Mathur, Software and System Technology, and Yotran Chen, Interfacial Processes, the makeup of one of the 3-inch MCT wafers. John has been fortunate to have had the opportunity to work with the MCT process line that also happens to be the Science Center's 1995 Team of the Year. Grace Ma, Materials Processing and Chemistry, has been studying the magnetic properties of radar-absorbing material using an instrument called a susceptometer. The measurement depends on the volume of the sample. Here, Grace, along with her advisor, Charles Hollingsworth, is showing Natalie Yuan, Software and Systems Technology, Rory Solomon, Electromagnetics, and Joseph Fletcher, Interfacial Processes, how she first determines the weight of a large piece of material. Grace then places the weighed material in a pycnometer and replaces the top. The pycnometer is a device that measures the volume of the sample. After Grace knows the weight and volume of this material, she can then determine its density. Unwinding the material, Grace shows Natalie, Rory, and Joseph its flexibility and smoothness. After she has determined the density, Grace can calculate the volume of the small sample. Grace has placed a small sample in a cup and is placing it onto the sample rod. Charles instructs her to lift the rod and insert it into the susceptometer. This instrument will measure the response of the sample to a magnetic field at different frequencies. At the end of the run, the data appears on the computer monitor. The information obtained will be analyzed and the results used to design better radar-absorbing materials. Brandon Wright's Structural Ceramics discusses with his advisor, David Marshall, a ceramic sample he has been working on. Brandon shows the ceramic sample to Lori Lee and Quincy Chin, also in the Structural Ceramics Department, and Mandana Kushnevison from Imaging Devices. Shown here is a cross-section of a new ceramic thermal protection system. This new high-temperature ceramic, called monazite, was recently discovered at the Science Center. Here Brandon is using a polishing wheel with a diamond-impregnated cloth to make a highly polished surface so the sample can be examined in a scanning electron microscope. This material may possibly be used on the reusable launch vehicles, which are replacements for the space shuttle, or perhaps the space shuttle as well.